So what we're going to look at today is now vertical circular motion. And vertical circular motion works different than uniform circular motion does. Okay? Adam, can I get you to turn those front lights back on for me, please? Okay? So in uniform circular motion, where we're going horizontally, the speed doesn't change. The speed is constant all the way around the circle. Okay? But if I make this circle vertical now, what happens to the speed? Where's the tape going the fastest? At the bottom, right? Because now we've added in an additional force. Okay? We've added in the force of gravity. Okay? Gravity didn't matter when this thing was going around and around horizontally. It was perpendicular, so it didn't affect the speed of the object. Okay? But when we're dealing with a vertical circle, okay, now it suddenly does matter. Okay? It'll accelerate it toward the downward portion and slow it down in the upward portion. Right? So you're going the slowest near the top and fastest at the bottom. Okay? Where do you suppose you would need the most centripetal force to stay in the circle? Because if speed changes, centripetal force changes. Like if, I mean, you guys aren't whirling this, I am. Okay, where does the tape feel the heaviest to me? At the bottom, right? Because that's where gravity as well as its inertia are working against me. So they're putting more tension in the rope at the bottom when they're both pulling outwards. At the top, I'm pulling inwards and gravity is pulling inwards. In fact, if I go just fast enough to stay in the circle, okay, look what happens to the string at the top. Right? Like there's no tension in the string at all if I go just fast enough to make that circle. Okay? All right, so we're going to be looking at how this vertical circular motion works. Okay? The most important part is this, that for a vertical circle, centripetal force is the net force. It is the vector sum of all forces. Okay? So basically what we do is we take any forces that are acting in and we subtract from them the forces that are acting out. And that'll give us a net force into the circle, which will be our centripetal force. Okay, so that's the formula you're going to use a whole bunch to do with vertical circular motion. Identify the forces that are acting in, identify the forces that are acting out, subtract them, and you've got your centripetal force. Okay. All right. Now, once in a while, you'll see somebody perform this trick where they, go through this vertical loop. Right? Roller coasters do it all the time, but sometimes you'll see somebody like ride a bike, okay, or something like that through a vertical loop. And it's tricky, okay? Because if you don't go fast enough, what happens? You fall back in. Okay, you fall back in. Like Homer, because Homer fell back in. Okay, so that's kind of how that would work. We have to achieve that speed in order to stay in the circle. So when the speed of, and obviously you're going the slowest here at the top, fastest here at the bottom. Okay, and either side you'd be about the same. Okay, so here's how a vertical circle works in terms of the forces that are acting on you. Okay, at the bottom of the circle, so let's say we're Homer and we're doing the ball of death thing here. Okay, gravity at the bottom is trying to pull you out of the circle. The normal force of the circle or of the cage is pushing me back towards the middle. It has to be bigger than gravity. Okay, otherwise I would fall out. On the sides, gravity pulls perpendicular, so it's irrelevant, and then you've got the normal force of the cage pushing you back. At the top of the circle, if I'm going just fast enough to stay in the circle, I would only have gravity pushing on me because I'm going just fast enough. We saw when I was whirling the tape around that the tape would actually go slack, right? The string would go slack when it was at the top. That means that there was no pulling force in the string anymore. So similarly, if I'm going just fast enough to stay in this circle, I'm just going to have gravity pulling me back down, and the circle isn't going to push on me at all. Okay? If I'm going faster than the minimum speed, then I am going to push on the circle, and the circle will push back, according to Newton's third law. All right, so we would have those two forces acting in then, and then again on the sides, gravity's perpendicular. Okay, so we actually don't do any problem solving to do with the sides. because they're the same as a uniform circle, which we've already done. So we deal with, excuse me, 3 different places. The bottom on the inside, the top on the inside, as well as the top of the circle on the outside. Okay, so if I'm on the outside of this circle on the top, gravity wants to pull me downwards, and what's pushing out? Normal force. Yeah. If I'm on top of the circle, normal force is pushing me out. Okay. If I go fast enough, what could happen at the top? On the outside. You could fly off. You've probably seen the stupid people who go over that big speed bump out here too fast. Okay, and their car gets dragged on the ground a little bit. Okay, that's because they're almost to the point where they would lose contact with the road, almost fast enough to jump over it. You're not going to do that. Okay, you don't want to. I've seen someone do it and they wrecked their transmission. Like literally, it was on the ground behind them. Okay, that car was dead. Okay. But yeah, if you go over the top of a vertical circle fast enough, you can lose contact with the circle itself. And as a result, you would feel what feeling? Weightlessness. Okay? Because you're a projectile. Like when you fall, do you feel your weight? You don't feel your weight till you hit something. Okay? While you're falling, you feel weightless. So essentially, if you go over the top of a vertical circle fast enough, you will experience a feeling of weightlessness. It's apparent weightlessness. It's not real weightlessness. You do still have weight. You just can't feel it because the normal force is 0. Okay? Remember, we don't feel the force of gravity. We feel the normal force, the reactive force of gravity. Okay? But we don't feel the force of gravity itself. So if I go over the top of that vertical circle fast enough, I will feel weightless. Right? And this is how that scene with him in the plane with the pen floating around was shot. Okay? NASA's Vomit Comet went over the top of a vertical circle fast enough that he experienced, at least temporarily, weightlessness, apparent weightlessness. All right, so do those forces kind of make sense? All right, so we were talking about how this is the formula, okay? Fc equals forces in minus forces out. All right, so we would take, let's say we're dealing with the bottom here, we would take normal force and subtract gravity, and whatever that number comes out to is what mv squared over r equals. And then we could solve for v or r or whatever. Okay? If we were on the top of the circle, it's like on the top on the outside, then gravity is acting in, normal force is acting out. So it would be gravity minus normal force. Okay? And oftentimes we use the term apparent weight for normal force. You might want to write that down because that's going to come up a lot. Okay, normal force is called apparent weight often. Okay, so if I go over this circle fast enough, then I get a feeling of apparent weightlessness because Fn would become 0. Okay, gravity would still be there. Okay, I'm just a projectile now, right? And gravity is trying to pull me back down. Okay. Making some sense there? All right. I'm going to show you a couple more videos here. The first one is from Cirque du Soleil. Did anyone seen Cirque du Soleil Cusa? A few years ago now. Mr. Dickey went and saw it, and he was so amazed by their wheel of death that he bought the DVD, and then we kind of, yeah. So, all right. So what we're looking at here, guys, okay, as any object goes around the vertical circle, okay, the magnitude of the normal force is what changes. Your apparent weight changes. Your real weight doesn't change because you're on Earth and gravity is always the same. So as you go through this loop, and this is like somebody actually does this. You know, you had those little orange circular tracks for like Hot Wheels when you were a kid. Okay, well, they do this with real cars. Okay, and so these guys they'll accelerate into this loop and they'll feel really heavy here at the bottom. Okay, this is where that kind of double gravity sensation they were talking about was. Okay. You feel much heavier than normal here, and then as you go around, okay, here you'd feel pretty much normal, okay, and then going around the top, you'd feel lighter and lighter, possibly even weightless if you're going slow enough, and then as you return back down, you'd feel that heavier sensation, okay. This is the kind of dangerous spot, the bottom of the circle, Okay? And I say dangerous spot because like on a roller coaster, or if you're a fighter pilot or something like that, it's pulling out of a loop that is the spot where you can black out, because that is where you feel heavier. Okay? Your apparent weight is greater. And depending on your speed and the radius of the circle, okay, you can experience G-forces there that could be upwards of 7 to 9 Gs. Okay, so you feel 7 to 9 times heavier than normal. And we talked about this earlier in the unit. Okay, G-force makes your everything in your body heavier, your blood, all of it, right? And your heart just can't pump blood to the brain if it's that heavy. And so it tends to drain away from the brain and you black out, right? On the mind bender, okay, at the bottom of the vertical loops, people sometimes black out. Okay? You pull about 4.5 Gs in the bottom of those loops. Okay, it's not unusual for people to black out. Okay, not so much the first time, it's pretty rare the first time, but if we get lucky and we get there on a day when we're the only people there, they'll sometimes just let us ride it consecutively. Okay, like they'll stop it and then, oh, there's nobody in line, boom, off you go again. Okay, we had a group of kids one time when we were on this that were able to ride it from one maintenance cycle to the next, which was like, I think it was like 40 minutes or something like that. They never got off. Okay, yeah. And they were like, by the second, third time, their heads are just bobbing around, whatever. They would stop, wait for them to kind of, okay, you guys are, yeah, let's go again. Because they were crazy. Okay, and we'd go over and over again. So it's doubtful that that'll happen again, but we were really lucky that one day we were the only people in the park that day. Okay. All right. So when we're dealing with these points in the circle, okay, remember that for any point in the circle, Fc equals the forces in minus the forces out, right? So when we're here, okay, our force in is normal force. And it's going to have to be pretty big because gravity is pulling outwards. Okay? So for that point there, Fc would be normal force, or if this was something on a rope, tension, okay, minus the force of gravity. Right? As we said up here, okay, we would have that Fc would be the force of gravity. Okay, if we're on the inside, and then if we're going fast enough, there might also be a normal force, but they're both pushing in. There's no forces pushing out on the inside at the top, right? And then we just saw a couple of videos about the outside over the top. Okay, on the outside over the top, gravity's still pulling in, but normal force is pushing out. Okay, and if we go fast enough, that normal force will become 0. Okay, everyone's okay with those ideas? All right, so riders who perform this loop-the-loop trick, or if you're on a roller coaster, okay, you have to have a certain minimum speed at the top of the circle. Otherwise, you fall out. Now, on a roller coaster, obviously, there's safety mechanisms in place. You wouldn't fall out of the roller coaster. Okay, it's clipped on both sides of the running pipe. Okay, so there's a wheel on each side, so it couldn't actually fall off. Okay, if it was hanging upside down, and that has happened sometimes on rides that something trips the emergency brake system and it'll break. Wherever you are in the ride, the brakes apply. Okay, that happens to be at the top of the circle. That's when you hang upside down for a while. Okay? You've seen the new National Lampoon's Vacation. That happens to them at the end. They get stuck in the upside down part of the loop. Okay, we got stuck at the beginning of the Mindbender once. Did I tell you that story? Good story. Okay, we go up the Mindbender. Okay, we're going all the way up the hill. We get just to the point we're about to drop down the first drop, and the brakes go on. We're sitting there like this, hanging, looking down at the first drop. We're like, not funny. What's wrong? Because we're kind of committed here. Like, there's like little ladders and stuff like that just off to the side of the track that you could possibly use in an emergency, but you're almost like, I'd almost take my chances on the ride as opposed to that ladder. So anyway, we're like, okay, they'll get us going in no time. I'm sitting next to one of my students, and he's kind of not real happy. I'm not, but I got to look like I'm calm, even though on the inside I'm like, I'm going to require a clean pair of shorts in a minute, right? Anyway, he's in this full-fledged kind of panic attack. I'm like, yeah, man, they'll get it going. They'll come on the speaker. They'll tell us what's wrong, hopefully, Anyway, 10 minutes later, I'm still sitting there. No one said anything. No one's coming up the ladder. Okay, we're just hanging there. He is pulling a Harry Houdini. He is halfway out. Okay, like there's this thing that comes down, a shoulder harness that comes down over you and latches in. And he has like done like the Mel Gibson Lethal Weapon, almost dislocated his shoulder in halfway. And I'm like, where are you going? Like, what are you, like, seriously, even if you get out, where are you going? Like, you're going to jump? Like, you got to stay in the seat here. I want out of here. I want out of here. Like, I want out of here too, but not that way. Okay. That's the way out, like, out of everything. Anyway, I get him calmed down enough that he's kind of gotten back into the shoulder harness, and then all of a sudden the brakes release and off we go. There were no screams on that ride. It was the quietest mind bender with people on it ever. We were just like, oh God, we're not going to die. Please don't let us die. Because we didn't have any idea, like, okay, the problem's fixed. I guess. Nobody told us anything, right? Then we get off, and they don't let anyone else back on. They throw sandbags in the seats, and they run it a couple of times. They're like, oh, someone really should have come to get us and let us off of there. Yeah, it's never happened since. Never been a problem. We've never had a problem since then. But of course, there was a problem in the very late 80s when they first built that, because it was all designed and fabricated in Europe, and all the pieces were sent to North America to be assembled. And so the people who designed and fabricated it all weren't there when the ride was put together. So they put the track together, and then they built the trains. The most specific instruction is that the trains can never be more than 3 cars long. Well, when they put it together, they made trains 5 cars long and went off the tracks. Okay? Riding in the front car is much different than riding in the back car. Okay? The back car, you whip around a lot more. Okay, like there's a lot more side-to-side kind of lateral forces. You can actually get a sore neck if you ride in the back too much, okay, just because you get whipped around a lot more. Well, imagine now you've got 2 more cars on the back. So they would whip around enough that they actually broke the locks off, and one of the cars came off, and it pulled the other ones with it. Okay, so yeah, read the instructions when assembling something, okay, even if it's from IKEA. I know they're not really helpful, but okay. All right. So if we're going through this loop, there's a minimum speed to stay in the loop, okay? And when we're at that minimum speed, we don't push on the loop at all, okay? So we just kind of go over the loop and we don't push on it. We would feel weightless. Almost no roller coaster does that. Roller coasters all go way faster than they have to, okay, in order to give you that G-force sensation. Okay, so you wouldn't probably ride a roller coaster where you would feel that way. Okay, I'll show you the one here, the Griffin, because the Griffin is like, well, the other ones aren't all that good. The Griffin one's probably the best of the 3. So I'll show you that one, and they've got a couple of vertical loops so you can see that going on. So we got what can happen if we're looking at just the minimum speed. So let's see if we can calculate what the minimum speed is for this roller coaster loop that has a radius of 9 meters. All right, so it's a vertical loop. We know that for any vertical loop, Fc equals the forces in minus the forces out. When we're at the top of the loop, okay, at the minimum speed, we're going just fast enough to stay in the loop, okay? Under normal circumstances, gravity would be pulling us down, and we'd be pushing on the track a little bit, so we'd have some normal force, except that we're going just fast enough to stay in the loop. So which one of those forces becomes 0? If I go just fast enough to stay in the loop, do I push on the loop? No. So the loop can't push back on me. And as a result, I would feel apparently weightless. Okay? There would be no normal force. Only gravity would be pulling me back towards the center. All right? There are no forces out. Okay? There's nothing trying to pull me out of the loop. So really, all I have is gravity. Gravity is acting as my centripetal force. So this is just like the artificial gravity questions we did the other day. Okay, so that'll be Fc equals the force of gravity, and that'll be mv squared over r equals mg. Okay, so we're trying to figure out what the minimum speed is. How slow can I go through this loop and still not fall out of the loop? Okay, so that's what we're trying to solve for here. All right, so we're looking for v. So we have r. R is going to move over here. If I divide both sides by m will cancel, and would be the square root of GR, which we said happens all the time in this unit. Okay, so we're going to have V equals the square root of 9.81 times the radius, which they told us was 9 meters. All right, so we're looking at 9.4 meters per second. Okay, so I would have to be moving at 9.4 meters per second in order to stay in that vertical circle. Right? That's pretty fast. That's how fast I have to be going at the top. Right? Wouldn't be all that hard to get going that fast near the bottom. The problem is to get to the top, you're going straight uphill. You slow down quite a bit as you go through the loop. Okay? That's why it's really difficult to do this on like a pedal bike or running. Okay? I've actually never seen anyone do a vertical loop running, but I heard it's been done. Okay? But you would have to run really fast. Okay? You would have to be a really, really strong runner because you're going to be running straight up for a little bit. Okay? And you got to run fast enough and not get scared like Homer and fall out of the middle. Okay, everyone follow what we did there? Okay, so all we did was forces in minus forces out. We just had to essentially draw a free body diagram like we would have in the last unit. Identify what force or forces are here and what direction they go, and then we know where to put them in that situation. Okay, okay, so that's what we just did here, so we're good on that. All right, so this one is just like what we just did. You guys give it a try. It has one small trick in it. All right, so the trick here is they give you the diameter of the loop. What do you need? You need the radius of the loop, so you just got to divide 50 by 2. Okay, so we have the top of the vertical circle. We're going for the minimum speed. At the minimum speed, only gravity is acting as a centripetal force. There's no normal force because we're not going fast enough to exert force on the track, so the track can't exert force back on us. So we're left with this as our forces in minus forces out. There's no forces out, there's just this. Okay, so then we have mv squared over r equals m times g. Okay, multiply both sides by r, m cancels, and we square root to get our minimum speed value. All right, so that'll be 9.81 times 25. All right, so you can see that as the radius of the circle increases, our minimum speed increases. Okay, when we were talking about a 9-meter radius circle a minute ago, the minimum speed was 9.4. Okay, now we've got a 25-meter loop, and we have to go 15.7 meters per second to stay in the loop. So if you were going to have someone do this on a pedal bike or running, okay, the circle would have to be pretty small. Okay, it would have to have a pretty small radius for them to be able to achieve it. Okay. All right, is that type of question making sense? Right. So it gets a little bit more complex if we deal with, let's say, this situation. Let's have you write this one down because you don't have this example. Okay, so the radius of this circle is 19 meters. I've got this cart going over the top of the vertical circle. Okay, the mass of the cart is, let's say, 100 kilograms. Okay, and that includes the people inside it. Well, then that's not right. Those are really light people. Let's say it's 200 kilograms, including the people inside it. Okay. When it goes over the top of the vertical circle, okay, the apparent weight of these people and their cart is 1,200 newtons. How fast is the cart going? Okay, so we're looking for V. Okay, we know the mass and we know their apparent weight. Apparent weight is which force? Normal force. Okay, so if we're looking at the top of a vertical circle, we want to essentially draw a free body diagram. Gravity pulls into the circle. Okay? Apparent weight acts out of the circle. And for all vertical circles, FC equals forces in minus forces out. Okay? So what we have is mv squared over r equals mg, which would be 200 times 9.81, minus our force out, which was normal force, 1200. Okay, so how do I solve for v in this situation? Can I manipulate? Can I just put this in brackets and say I'm going to do all of that first and then move this other stuff? Sure I can. Okay, I'm just going to multiply both sides by r, and then I'm going to divide both sides by m, and then I'm going to square root. Okay, and I'll have how fast the cart needs to be moving to give them an apparent weight of only 1,200 kilograms when their actual weight, okay, would be like 1,962. Okay, so I'll have a look at what that's going to come out to. Whoops, that's not 200. Okay, and then we want to square root that. Oh, I didn't multiply by the radius. Right, sorry. 762 times the radius, which we said was 19 meters. Okay, we have that. Then we're going to divide by the mass, which was 200. All right, and then we're going to square root that. Okay, so the cart must be moving at 8.5 meters per second as it goes over the top of the loop. Okay, and you've probably all experienced this. If you've ever gone over, like a kind of a, a small hill in a road, you get that feeling of that, like your insides are kind of moving towards the top. You get that like heart in your throat kind of feeling. Okay, that's because of this. Okay, your apparent weight is less than your real weight. The inertia of all of your, internal organs is kind of to keep going, and then you're attached by a seatbelt to the car, which is pulling you downwards. Okay, so you get that feeling, right? And obviously, if you go fast enough, you could launch off of the top of this vertical circle. Okay. All right, making some sense. That's probably about as complex as they would get. Okay, like a vertical circle question won't get much more complex than that, unless I was to say they feel 4 times their normal weight. So I don't actually give you a number, I just tell you they're 4 times heavier than normal. Okay, well how do I calculate what 4 times someone's weight is? Will that work? Right, 4 mg, right? That's 4 times their weight. Okay, I'd be able to do it that way. Okay, I want you guys to try those 2 to finish off here.